So we saw how atoms make hybrid orbitals to form equivalent bonds or bonds to atoms. Let's look at how we would evaluate how we know which hybrid orbital we have and how we would describe, using valence bond theory, the bonding within a molecule such as BF3. So these are the orders this is the order we're going to do things. We're going to write the Lewis formula. From the Lewis formula, use Vesper. From the Lewis dot structure, we'll use Vesper, PR, to model the arrangement of electron pairs. Around the central atom and within the molecule. Okay. From the electron pair, arrangement, we can ask ourselves which orbitals, hybrid orbitals, are needed. Okay. Then, so with this, we'll be able to figure out the hybridization that's involved, and then to describe that determines the hybridization. And then the next two steps will describe the bonding in the molecule. Okay, so the next two steps would be to assign valence electrons to hybrid orbitals. One atom at a time until, we'll assign valence electrons to hybrid orbitals, one atom at a time, only pairing when necessary. And then we will form bonds by overlapping single occupied orbitals of other atoms. So in other words, atoms that only have one electron in each orbital, they'll be able to do the overlapping. So let's do these steps, determine the hybridization and describe the bonding in the molecule for the BF3 molecule. Okay, well, write the Lewis formula. So now we're putting everything together that we've been doing in the last several chapters. We would have counting the total number of electrons. We would have 24 total electrons, the best Lewis formula. And I encourage you to just stop the video here and do this, or if you haven't already. The best Lewis formula looks something like this. Okay. We're going to use this table that we constructed during the last video, in the last lecture video. This is a trigonal planar geometry, electron pair geometry. 3 places we're putting electrons. That means that the boron is sp2 hybridized. Since the boron is sp2 hybridized, so let's draw a diagram and just describe the bonding that's happening between the boron and the fluorine. So I'm going to draw these a little different. The energy is going to go up. Oops, we have the 1s. Here's the boron atom. 2s and the 2p. So boron, I have one electron in the 2p. The boron atom is going to hybridize. The s and 2p orbitals, right? If you're trigonal planar, you're using 1s and 2 p orbitals to make 3 orbitals. So it would look like this. From an energy perspective, just haven't mentioned this part. The hybrid orbitals are going to be slightly lower in energy than the 2p, but higher in energy than the 2s, which makes sense. Remember, we took these 3 orbitals essentially and made them equal, and they're going to meet each other in the middle with respect to energy. So our energy, or our diagram would look like this for the boron atom, and now we have 3 equivalent orbitals. 3 equivalent orbitals. It's a trigonal planar electron pair geometry. Since it's a trigonal planar electron pair geometry, we know it's sp2. And what we have is something like this. We have a trigonal planar arrangement, sp2 hybrid orbitals. There are 3 equivalent ones in a plane that each fill the lobe, or each lobe is on the apex of a equilateral triangle. Okay, so now we have these 3 equivalent orbitals, and what's going to happen is the fluorine, which has a p orbital that's free, is going to essentially come in with its p orbital and share each one of those electrons. Each three fluorines are each going to share 1 electron and overlap the 2p sp2 hybrid orbitals. So we'd have something that would where we have the sp2 hybrid and the p orbitals of the fluorine, the valence orbitals of the fluorine, overlapping to make our bond. So that gives us an idea of how we would describe bonding using valence bond theory and hybrid orbitals. It's an overlap of orbitals. Now you might be asking, what about multiple bonding? Okay. Well, what if there's more than 1 orbital from each bonding atom that overlaps? So 1 hybrid orbital is needed for each bond. And it turns out, so with respect to multiple bonding and this, there are 2 types of bonds. Sigma, that's the small Greek letter S, right? Sigma, S-I-G-M-A. We have sigma bonds, which have a sort of a cylindrical shape about the bond axis. Or the electron density is between the nuclei of the atoms in the bond. That's a sigma bond. There's another type of bond that we can have that we'll see in a moment here. Pi bond. A pi bond, the electron density is above and below the bond axis. Now, to illustrate this, we're going to look at 3 different molecules. Oops. C2H6, C2H4, and C2H2. Okay, so this is you don't need to know this, but you'll next year you will in organic chemistry. This is ethane. This is something called ethylene, and this is called acetylene. All right. So let's draw Lewis structures for each of these. So in ethane, our best Lewis structure would look like this for ethylene. And for acetylene, we have a triple bond. Now our goal here is to be able to talk about the bonding of each of these in a context of valence bond theory. Let's first think about, let's use valence bond theory to describe the bonding in each. Okay, let's first think about ethane. What would be the hybridization, or what would be the molecular geometry? Let's do the steps that we just talked about. We're going to write the Lewis formula, which is what we just did. Use the Vesper model to arrange the electron pairs. That's what we did. And think about it. From the electron pair arrangement, which hybrid orbitals are needed? Okay, so let's look at this first. So we have 4 places we're putting electrons around this central atom. The electron pair geometry. So in ethane, C2H6, both carbon atoms have a tetrahedral electron pair geometry. There are 4 places around each carbon we need to put electrons. And they all happen to be bonding electrons. What this means is that we have the carbon being sp3 hybridized. If we know the electron pair geometry, we know its hybridization of the central atom. So each carbon in this molecule is sp3 hybridized. So each carbon atom, if we were to draw what it might look like, what we have, these are sp3 hybrid orbitals. There are 4 of them. They are equivalent. They occupy the space of the apex of a tetrahedron. In this case, 3 of those hybrid orbitals overlap with a hydrogen 1s orbital. And with the other orbital, we have overlap between the other carbons, sp3 hybrid. So both carbon atoms are sp3 hybridized. They're using one of those hybrids to bond to each other, and the other 3 hybrid orbitals are being used to bond to the hydrogen. Let's think about use valence bond theory to talk about ethylene. Contrasting these 3 things, let's think about ethylene. C2H4, what we have going on we know. So what's the so what would be the electron pair geometry of a carbon atom in this molecule? Well, there are 1, 2, 3 places around each one we need to be able to put electrons. Recall that valence shell Vesper theory tells us that we treat multiple bonds as single bonds. So there are 3 places we're putting electrons around that guy. That means that the hybridization of that central atom is sp2 because it's a trigonal planar geometry, electron pair geometry. So electron pair geometry for each carbon is trigonal planar. Since it's trigonal planar electron pair geometry, automatically we know carbon is sp2 hybridized. So what we have with each carbon is a trigonal planar arrangement of the sp2 hybrid orbitals. So I'm going to draw the other carbon atom. So these are going to be our sp2 orbitals, right? Let's draw the other carbon. Also has 3 sp2 hybrid orbitals. Okay. But note here that recall, if we made sp2 hybrid orbitals, we used 1 s and 2 p orbitals. There's still 1 p orbital left. That's there. The 1p orbital remains unhybridized. That p orbital has a shape, we'll put it right here. What's going to happen with that p orbital, the one that's left? This is a 2p orbital. Here's a 2p orbital. These guys are going to overlap to form that second bond. Now, if you recall, we had 2 different types of bonds that we were talking about in this section. We had sigma bonds and pi bonds. Sigma bonds, the electron density falls between the atoms. Pi bonds, the electron density falls above and below. Now, if we think about what's happening here, the electron density of that's due to the bond that's due to the sp orbitals, the electron density is between the 2 carbon atoms, whereas the electron density of the p orbitals is above and below. Here's a slightly better picture of the same thing I'm trying to draw from your textbook. The pi bond or the sigma bond framework in ethylene looks like this. So one thing we didn't draw in yet are the 1s of the hydrogens bonding to the two sp2s of the carbon. But what's happening is the sp2s are overlapping, right? Just like our picture here. And the remaining s orbital, the remaining orbitals, the remaining 2p orbitals form what's called a pi bond. They form that second bond. The electrons are above and below the axis of that molecule, however, and so it would be a pi bond. So what we would say is the sp2 orbitals are overlapping. How many? So in this case, we would have one sigma bond between the two carbons, but there are a total of 3 sigma bonds per carbon, right? It's bonding to a hydrogen also. All right. The next one, let's think about the molecule acetylene. Now, with acetylene, things get a little more complex to draw. Things get a little more complex to draw. But what we have here is, and I'm going to use the image from your textbook to show this. But with acetylene, let's first draw the Lewis structure. Let's follow that chart I gave us for figuring this out. So our first step is to write the Lewis formula. We're going to use VSEPR to figure out the arrangement of electron pairs. Here we have how many places around the electron we're putting, or around the central atom we're putting electrons. Well, there are 2. The electron pair geometry around each of those carbons is linear. That means that each carbon is sp hybridized. And we see that here. It's sp hybridized. It has taken one s orbital and one p orbital and made 2 equivalent orbitals, and its hybridization would be sp. Since we only used one s and one p orbital, one s and one p orbital, there are 2 p orbitals unhybridized that are still around to be able to make bonds, and those are going to form the pi bonds within acetylene. And so we would say that each carbon is sp hybridized. The bonds formed by overlapping the sp, the sigma bond formed by overlapping the sp between the 2 of each of the carbons, and the 1s and the sp for the hydrogen in the carbon. And then the pi bonds are formed. Remember, pi bonds, the density is above and below the axis of the bond, above and below that. And there we have how we would talk about valence bond theory to describe these, and hybrid orbitals to describe the bonding in these molecules.